today. So let me, before we begin the interactive session and we invite groups one by one to present their section of the material, let me give you a few principles that we need to follow in this session. Remember, this session is meant to introduce the material. That means we are not trying to teach all this material in a span of 1.5 or 2 hours. It's impossible. How can we expect to teach what is taught over 5 hours in 1.5 hours? We'd only do a shoddy job. So this is our skill here as teachers. We need to identify the crux of each section of the pedagogical material. And we need then to present it before our audience of colleagues, of teachers, in such a way that all of us get to know what that lecture contains and what are the salient features that are brought out in that lecture or in that demonstration or in that session. And as you know, we have 10 sessions to deal with today. So if I go by that principle, then I should be able to devote about 8 to 9 minutes per lecture, or that means 8 to 9 minutes per group, isn't it? Because we have got 90 minutes and we have 10 groups and essentially 10 sessions or 10 lectures, you may call them that. And we therefore have about 9 minutes, 8 to 9 minutes, we would say, per session, per lecture. What should you be doing when you make a presentation as a group? You should be bringing out what that part of the lecture or that part of the course aimed to teach. You should bring out certain salient features that you would adopt when you teach that part. You should bring out some further thoughts that you might have had when you listen to that lecture. You might also want to bring out what pedagogical strategies you would adopt. Now, of course, I know it's all difficult to do this in 8 to 9 minutes, but do as much as you can. And don't worry about, trying to go in a hurry, but then also don't prolong your presentation too much. Strike a balance. I know this is the first interactive session. It will take us some time to get used to it. Don't worry, even if we can't finish all the lectures now, we'll finish them in the afternoon session. But as far as possible, let's try and deal with as many lectures as we can in this interactive session. And therefore, without further ado, I would now like to start immediately. Start afresh and start immediately. So I would be very happy now to welcome Group 1. Now, before we begin the presentation, may I request Group 1 to come forward and introduce themselves. So any one member of Group 1 could come forward and introduce himself and herself and his or her partners, right? And then begin the presentation. We will then allow you to make a presentation. Yes, if you wish to use a presentation screen, it's fine. Otherwise, you could use an oral, you could just orally explain what you're trying to explain. So with that little introduction, let me now welcome Group 1. Yes.
Okay, can I proceed, sir?
Yes, please. Yes. May I introduce yourself, introduce your group partners, and then proceed. Yes, and then tell us how you're going to go about it in 1 minute.
Yes.
Yeah, and then proceed. Yes.
So very good morning to all those who are present here. Myself, K. Ramachandra Reddy. I belongs to Group 1. So my group members are myself and Rajeshwari Madam and Seema Diwan Madam, Laika Das Madam, Chandrakant Pal sir. Okay. So we five belongs
very warm welcome to all of you, and we look forward to your presentation.
Okay. So regarding to our presentation, we're going to discuss regarding to the abstraction, which we are getting the information from the SAR's first lecture. Okay. So now I'm going to present my screen. Very good morning once again to all. So for batch number 1, we're going to speak regarding to the introduction to abstractions. Okay. So before going to these things, first we have to know about what is meant by signal, what is meant by system, how we're going to interrelate with each other, and then where it is applicable. Okay, fine. So regarding to signals and system, it is not only related to the electronics part, it may be used in the biomedical, seismology, acoustics, or energy generation, distribution, robotics, control systems, wide variety fields over there. Okay. So in general, wherever you're using this kind of signals and systems, okay, in broad concept, we're going to speak only about the very two important features about the signal. Okay, so regarding to the signal, it is nothing but a physical quantity. It contains some information in any area, whether you're taking a control system or something else. So signal is nothing but it is a physical quantity. It contains some information, and it's going to varies with the some independent variable like time, space, pressure, temperature, density, pressure. All those things belongs to the some of the independent variables. Okay, fine. So again, if you want to say like this also, a signal is set of data or information. It contains a function of independent variable. So here in this course, you are going to deal with the corresponding independent variable is nothing but time. Okay. So we are going to speak regarding to the a signal which it is a function of independent variable time here. Okay. So here we are going to discuss about the one dimensional signal. So regarding to one-dimensional signal, that is nothing but the corresponding independent variable is going to be the only one. Suppose if we're having two different independent variable, it belongs to the two-dimensional signal. Suppose we're having more than two, it belongs to the multi-dimensional signal. Okay. So regarding to the signal, it may be electrical signal or mechanical signal or acoustic signal, whatever it may be. So in general, a signal is nothing but it is a physical quantity which it contain some information varies with the time, space, and other independent variables. Okay, fine. So some of the examples related to the signals of speech signal, video signal, a noise, voltage, as well as the EEG, electroencephalograph, ECG, electrocardiogram. These are some of the examples related to the signals. Okay, okay, fine. So the next thing. Regarding to the continuous time signals. Okay, so the better example for continuous time signal what we are speaking now. Okay, speech signal is the best example for the continuous time signal. So regarding to continuous time signal, the corresponding independent variable is nothing but time. So we're going to represent a continuous time signal with the help of x of t. So the general representation for continuous time signal x of t over here. Okay, so here t is nothing but independent variable. So regarding to continuous time signal, it is defined at any instant of time. So there is some defined amplitude will be there at any instant of the time over there. So here the independent variable time t varies from minus infinity to plus infinity. Okay. So regarding to continuous time signal is defined at any instant of time. So there will be some defined value over there. Okay. Another set of signals is nothing but discrete time signals. Okay, discrete time signal. In the name itself, it suggests that it is defined only at the discrete instant of time. So, for example, if we're taking a continuous time signal, you can define infinite number of possibilities between from one value to another value. For example, if we're taking from 0 to 1, you can define some infinite number of values over there. For example, just take on signal for example, I'm saying, okay.
Nice.
So here the independent variable is nothing but t. I'm going to represent a continuous time signal with the x of t. Okay. For example, just look at on this thing. Here t varies from minus infinity to plus infinity. So I'm not taking any values over here, but just look at on this thing. Suppose in between 0 to 1, I can able to define infinite number of values over there. So regarding to continuous in time signal, there is some particular defined value wherever taking the some particular time over there. For example, 0.01 also there will be some defined value. Point not Google number of zeros followed by 1. They're also having some defined value over there. But in the case of discrete time signal, try to differentiate these things. So this is all about this course. Okay. So regarding to discrete time signal, it is defined only at the discrete instant of time. So for better example, number of days per a week, okay, number of months in a calendar year, like that, and I can say those things. For example, Now try to differentiate these two things. So regarding to discrete time signal, it is defined only at the discrete instant of time. For example, if you're taking continuous time between 0 to 1, you can define infinite number of values at that. Okay, it defined at any instant of time. Regarding to discrete time signal, it is defined only at the particular instant of time over there. That instant must be the integer value, that you keep it in mind. Okay, so regarding to discrete time signal, it is defined only at the discrete instant of time. So if we're taking the values between 0 and 1, it is defined only at the 0 and 1. It is not defined in between these two things. Okay, but in the case of continuous time, you can define infinite number of possibilities between one value to the another value. So try to differentiate between continuous in time and discrete in time. Okay, so regarding to continuous time signal, you are going to represent with the this parenthesis the sign like this. Okay, x of t. So here t is belongs to the independent variable. Suppose if we're taking some pressure is independent variable, you can take it as x of p over there. So here it is varies with respect to pressure. For better example, when you're riding an automobile, okay, like two-wheeler or four-wheeler, so based upon the acceleration we are applying on the pedal, so based upon those things, the speed of the vehicle is going to be the varies over there. Okay, so the input is nothing but over there how much pressure you are applying on the accelerator pedal. According to that, the speed of the vehicle is going to be the changes. So better example for the continuous time, those things over there. Okay, similarly regarding to discrete time, we are going to represent with the square brackets. So here n represents that n number of samples. Okay, n number of samples. So the better example, total number of participants attended in this course. Okay, you can't able to say 20.45 members are attending, 24.34 members are attending. Okay, some number, some 30 members or 40 members or 70 members like that. Okay, so regarding to discrete time, it is defined only at the discrete instant of time. So try to differentiate between what is meant by continuous in time, what is meant by discrete in time. So in the both the cases, the independent variable is going to be the time. In continuous time, you are going to represent with the t. In discrete time, you are going to represent with the small n. It denotes that n number of samples. Okay, so again we'll discuss how to convert into continuous to discrete in the forthcoming classes. Okay, fine. Another thing, some of the example related to the discrete time cycle, population, number of persons attending the course, and so on. Okay, so you can take any electrical system. For example, in the course are told that we know already the three basic passive elements: resistor, inductor, and capacitor. So if we're writing the relation between those two things with respect to voltage and current, for taking resistor, V equal to I into R. V is proportional to the I here. Okay, fine. So here, when you're writing the voltage, V equal to L D over dt I of t. See, remember this thing. So here we are going to measure voltage across the inductor. That is also function of time. The current I of t, that is also function of time. Okay, so V of t equal to L d over dt of I of t. So regarding to the capacitor, I of t equal to C d V of t by dt. So if we're taking any system, it is contain input as well as the output. Okay, so regarding to system, that is nothing but it is a physical device. So it is going to process the corresponding input signal and it yields to the respective output signals over there. Okay, so regarding to continuous time system, the respective input as well as the output both are in the continuous in nature. Regarding to discrete time system, the corresponding input signal, the corresponding output also discrete in nature over there. Or you can also call like this. Okay, you can able to say input signal or excitation, output signal or response. Both are give the similar meaning over there. And in addition to those things, try to know this thing. So system is nothing but a physical device to perform some specific operation on the given input, some modification. For example, If we're taking the relation between voltage and current in the passive element resistor, directly proportional, V equal to I into R. If we're taking here time derivative, here also time derivative here. Some specific operation on the applied input over there. So here differentiation with respect to time, the corresponding current I of t. So here also to attain the current I of t equal to time derivative of the corresponding voltage V of t here. Okay. So here without applying input, it is impossible to expect the respective output over there. So it is not only restricted for the electrical system, you can able to apply in the control systems and all the fields wherever it is necessary. Okay, fine. And then, so when it is processing the input signal, there is some changes takes place related to the output. Okay, so for example, y of t equal to d by dt of x of t. What's the meaning over there? Time derivative of the corresponding input signal, or y of t equal to integral over x of t dt. So we're going to performing integration on the applied input, we're going to get it as output over there. So here the system is going to perform some specific operation on the input. Suppose if we're getting output is exactly equal to the input, that such a system is called as identical system. Both the input and output are similar with each other. Such a system is called as identical system. Okay, fine. Then so black diagram of the continuous time system. So here you're taking the input as well as the output, both are in the continuous in nature. So I'm going to represent mathematically general representation of the input signal x of t. So when I'm applying to the system, some transformation takes place to the respective input signal over there. So that I represented the mathematically some transformation of x of t, that is nothing but output over there. So just remember this thing regarding to continuous time system. The both the input and output are continuous in nature. Okay. Similarly, for going for the discrete time system, the corresponding input and the corresponding output also discrete in nature. So some transformation of input x of n, that is nothing but you are going to get it as the corresponding response y of n here. Okay. Okay, fine. So in this thing, we are going to discuss about the what is meant by signal, what is meant by system. So why it is called one dimensional, why it is called two dimensional, why it is called three dimensional, what is meant by continuous time system, what is meant by discrete time system, all those things. So we'll have some questions on those things. This is a pedagogy I would like to follow with the help of our batch suggestions. Okay. So you can answer for this question. Okay. First question, which of the following variables are independent? Okay. Post your answer in the chat box. Time, space, density, pressure, temperature, and all above. Okay. Space. Okay. So all these things are belongs to the independent variables. Okay. Time, space, density, pressure, temperature. Okay. This all belongs to the sum of the independent variables. Okay. Fine. So if a signal is dependent function of independent variable time, it is called as, suppose continuous means continuous time signal. In the case of discrete means discrete time signal. Okay. Suppose if the signal is a function of the independent variable space, nothing wrong in those things. Suppose if the signal is depend upon both time and space, it belongs to the two dimensional. All these three dimensional, all the above means multi-dimensional things over there. So here time, space, density, pressure, and temperature, some of the independent variables over here. Okay. So the correct option is nothing but F is the correct option. All the above are belongs to the independent variables. Okay. Fine. The next question. Speech signal is one dimensional or multi-dimensional? Any answer for this question? Speech signal. One dimensional. Very good. Good. So can I know? Okay. Just say whether it is true or false. Okay. So regarding to the speech signal, we are going to represent acoustic pressure variations as a function of time. Acoustic pressure variations as a function of time. Is it true or false? I'm asking. Regarding to speech signal representation, we are going to represent the respective acoustic pressure variations as a function of time. Is it true or false? I'm asking. True. Good. Very good. Next question. It can be represented with how many independent variables? I'm asking. Monochromatic picture. Okay. It's a function of how many independent variables? I'm asking. Two. Good. And the last question. The total population can be represented with continuous variable or discrete variable. Discrete, good. So this essence regarding to the discrete time signal. Okay, so regarding to continuous time signal, you can represent at any instant of time. So regarding to discrete time, it is defined only at the particular instant of time. That must be the integer value that you keep it in mind. Okay, okay. So thank you so much for giving this opportunity for me to present in front of all the faculty members. If there is any mistakes on my side, please excuse me. Okay. Thank you, sir, for giving this opportunity for me to present in front of all the faculty members.
Yeah, very good. Very good, Professor Ramchandra Reddy. I'm very happy with the attempt that you made. Now, very nice. Now, see, I didn't want to disturb the presentation in between, although there were thoughts that came up, when I was listening to the presentation that Professor Ramchandra Reddy made. First and foremost, let us all appreciate very warmly the presentation made by Professor Ramchandra Reddy. He's the opening batsman, so to speak. He's been the first one to deliver a session in this course. So definitely, he took up a big challenge, and a young man took up a big challenge to face all these colleagues and make a very interesting presentation. I was very happy with his attempt. So very well done. Let us now critically review his presentation. You see, let me first make a few critical remarks, and then I would also invite others to do the same. See, the aim of making critical remarks is not to belittle a colleague, but to point out how we can make a more effective presentation before a student audience, isn't it? Or how we can convey the ideas a little better. Now, first and foremost, I will first ask a few questions to all of you, and I would like any of you to respond, right? Do you think this presentation which Professor Ramchandra Reddy made brought out some of the essential aspects? The title of that lecture was Introduction to Abstraction. So do you think there was one important issue about abstractions which was missed in this presentation? May I hear from people? So any of you can come forward and speak. Introduce yourself and speak.
Sir, I would like to make a comment on this. This is Seema Behra from Bhubaneswar.
Yes, Professor Seema, yes.
Yeah, actually, I saw a couple of them, the presentation that you have uploaded on the IIT Bombay site.
Yes.
And abstraction has to, it essentially means you have to generalize the concept. And here I didn't see any generalization. That is what was missing. We have to generalize it. One single signal system applies to one single concept, applies to various kinds of systems. It has to be that way.
Yes.
So that is missing, I think.
Very good. I'm very happy to note that Professor Behra.
When I got it from your slide. I learned it from you, sir. So, thanks to you. But actually, that is what I see missing. What I learned from the slides that I saw, and then what I saw here, that was missing. It's not abstraction. It is only definitions. We just have definitions.
Yes. In fact,
even the first question, sir, I should Professor Ramchandra, please don't take it as a criticism. But even the first question, it was not very apt, I guess, because why should we ask what is independent variable? Anything can be independent variable. I mean, that question was, for me, I'm not saying that maybe for students it's good, but independent variable, anything, even I can be an independent variable. Even that way, mathematically, if you see. So even, this is what my remark. Thanks if I made a point.
Yes. So now, as I said, so Professor Ramchandra Reddy, none of us should take these criticisms personally. They are meant to improve our pedagogical skills, right? So I'm very happy that Professor Seema Behra brought up these points. Let us look at the academic content. Now, I fully agree with the point. You see, first and foremost, yesterday also I hinted at this. When we talk about abstraction is moving from what we can see, hear, feel, touch, to something that we can't quite see, hear, feel, touch. Why should we be doing it? As Professor Seema Behra says, why should we be doing it? We do it because we gain something from it. What do we gain from it? We gain that we can deal with many different situations at once. Now, this point should have been brought out more clearly in this presentation. And in fact, I'm emphasizing this because when you are speaking to a student audience, if you don't bring this out, the students will be turned off in the first lecture. Why are we talking about these abstractions? So it's very important for us to bring out the need for abstraction. You see, the word abstract actually means to bring out. That means to bring out what is common to many situations and leave out what is particular to some situations so that we can deal with many situations at once. Let me give you an example. You see, you can have an abstraction of how you prepare tea. If you wish to prepare a cup of tea, what do you need to do? You need to boil water. And then, of course, you need to add tea leaves to it. And then you need to add, a spot of milk, and then some sugar, and perhaps some, you may want to add some garnishing. Like, for example, it may be some lemongrass leaves, or you may want to add some coriander leaves, or you want to add some ginger, isn't it? So this is an abstraction. Now, in a concrete, it doesn't matter whether you're heating the water with a gas flame or you're heating it with an electric heater, or, you're grating the ginger with a grating device, or you're just cutting it with a knife or whatever. So those are the particular situation in which the tea is prepared. So, you abstract the preparation of tea by bringing out steps. Now, that is also not a full abstraction. So abstraction again has different levels of abstraction possible, isn't it? So you can say prepare a cup of tea or prepare a hot beverage. It could be a cup of tea, or it could be a cup of coffee, or it could be a warm soup, isn't it? So you want to prepare a hot beverage. That's also a higher level of abstraction. Or maybe a hot glass of milk with turmeric. So this is a higher level of abstraction. So, there are levels of abstraction as well. Now, why do we go to levels of abstraction? Abstraction is important because it helps us deal with many different situations at once. And therefore, the student needs to know that by learning how to abstract, he is gaining in the process, not losing. He is not losing sight of the physical reality. He is gaining sight of many physical realities at once. This point should have been brought out a little more carefully, I feel, in this presentation. And I'm saying this because when well begun is half done. So when you begin a course on signals and systems, unless you bring out the importance of abstraction properly, your students will not be with you afterwards, isn't it? So Professor Ramchandra Reddy, do you see what I'm saying?
Yes, sir. Yes, sir.
Yeah, very well tried. Don't take it personally. And also I agree with Professor Seema Bera that the first question could have been better framed. See, independent and dependent depends on the situation. For example, based on temperature, there could be some other quantity that varies. So temperature could then become an independent variable, and the other quantity could become a dependent variable. So for example, the pressure might vary as a function of temperature, in which case temperature is an independent variable and pressure becomes a dependent. So the dependence and independence is also a function of the situation. Also, there was a little bit of confusion in the presentation between continuity and discreteness in the context of the dependent variable and independent variable. So for example, your example of the months in a year is okay. So for every month, you may want to see what the population in a city was. There, the month is a discrete variable, and the population is also a discrete quantity. That is true. But you see, in every month, there might also be an average temperature, which could be a continuous quantity. So, the independent variable can be continuous or discrete. The dependent variable can be continuous or discrete. This is important. So, there are 4 possibilities, right? Is that right, Professor Ramchandra Reddy? So, there are 4 possibilities.
Yes,
is that right? Yes. So, this should be brought out a little more clearly. Now, before we go on to the next presentation, I still invite a couple of others, because it's very important for us, in the initial part of the course, it's very important for you to catch your audience, student audience. So let us spend a couple of more minutes in critically reviewing the first presentation. I can see Professor Ashish Mal has something to say. Yes, Professor Ashish.
Good morning, sir.
Very good morning.
I think the abstraction is basically kind of the level of detailing, okay, depending upon the level of complexity. For example, if I view the NIT Durgapur, for example,
Yes.
where I'm working, it's an university. So university is an abstraction. Okay, then if I go into the detail, NIT Durgapur has different departments, different offices, and so on. Then if I go further, the department has different labs, different classrooms, toilets, etc., etc. Then if I go into the lab, probably it's a communication lab, it's a signal processing lab. Signal processing lab has several equipments and so on. You can go into the equipments further, cheap, and so on. So it's all depends upon. To me, I think it's the level where you want to abstract the system or I don't know, the reality. Okay, it all depends upon the level where you are trying to see, visualize it. Okay,
Right.
so it is based on kind of complexity or the kind of detailing you want to see. Okay, and with regard to the I think there was a issue like the which is one-dimensional or multi-dimensional. It all depends upon the context. You have rightly pointed out that it's all depend upon the context. I cannot say that pressure is independent. Okay, the pressure depends on the temperature. Okay, in case of a pressure cooker, for example, how you are applying the heat. Okay, at what time you are measuring, and so many factors are involved. So I cannot simply say that pressure is an independent variable. Okay, that's it, sir. Thank you.
Very nice. Thank you, Professor Ashish. And in fact, yes, I agree with you. Abstraction also brings in a level of detailing. That's a very nice way of looking at it also. How much of detail should you include? Now, for example, you talk about a system. A system is a mapping from signal to signal. This point should have been brought out a little more clearly. Now, you see, which signal to which signal? For example, you can say an acoustic system, in which case the signals are acoustic signals. Or it could be a pressure measurement system, right? In which case the pressure input is the input signal and the measured value is the output, right? And of course, it could be discrete or continuous, whatever. But you see, what I'm trying to say is that the level at which we wish to look at the detail in the situation tells us how much of abstraction we want to do. If we want to remove a lot of the detail and keep what is essential to our discussion, we are doing more abstraction. If we are keeping a lot of the detail, we are reducing the abstraction. That's a very nice way of looking at it. Very nice indeed. Yeah, anybody else would like to make a comment on the first?
Yes, sir.
Yes.
Sir, this is Prema.
Yes, Prema. Yes,
sir, one more very important point he missed.
Yes.
Which is composite abstraction. It is basically trying to find out analogous systems, like how you explain the mechanical system and an electrical system with the help of differential equation. And another very good example is Newton's law of gravitation, where the apple falling to the earth and the moon revolving around the earth. So these two are two analogous systems. So composite abstraction is one point which he missed, which was very important.
Very nice. Yes. So, the idea of composite abstraction, that's also, one must say a little more about the nature of the abstraction. Yes. Anyone else?
Sir, this is Meenakshi Atre.
Yes,
Can I say something?
Yes, please. Yes.
Yes, sir. So I would like to give one more example. Right now, we have Python programming language.
Yes.
So that is also at an abstract level, because students don't need to go in the details of it. So all the toolboxes are ready, and then just they can pick and place kind of thing. So it's like at abstract level. So people don't need to go in the details. So abstraction is something like at very high level. You don't need to go in the details of it. So if you want, you can go, but C++ is nothing but at complex level. So on top of it, it's been built. So abstraction is we can say it's the helicopter view. So it's only the overview. So at a higher level, so you don't need to go in the details of it.
That's right. In fact,
Oh,
when you,
thank you, sir.
very nice. Thank you, Professor Meenakshi Atre. In fact, that's a very interesting analogy. And an abstraction is like a helicopter view. So, you know, when you're sitting in a helicopter, you see a lot of the scenery at once, but you don't quite see the details. That's very important. But you're able to see a lot of things at once. That's what abstraction allows you to do. So that's a very good example. All of you can take that as an example when you explain to the class. When you want to do abstraction, you're trying to look at it from a higher level. And she gave the example of abstraction in the context of programming. You can do assembly level programming, which is very, very detailed level, or you can go up to the level of C++ or C, or you can even go to the level of Python or whatever, higher, what you call an interpreter kind of situation, like MATLAB perhaps, or Python. And you know, so there are different levels at which you would deal with the variables, registers. You know, in assembly, you're going right down to the level of which register and which variable, you know. Whereas in the higher interpreter level, you're not so worried about which register. Is that right, Professor Meenakshi Atre?
Yes, sir. Yes, sir.
Yes.
Exactly.
So
Correct. Thank you, sir.
Yes.
Sir.
Yes. Yes. Yes.
Good afternoon, sir.
Yes.
On the line of Atre, madam, actually it is related to like something high level language and your low level language.
Yes.
So whatever you are writing on a C, that is a structured language, whereas inside you are not going, like rightly said by you, that in this machine level language, we can actually go that register by register, whereas in higher level language, we are not going according to it. Correct. That is one. The second is related to the practical example, like take an example of a MATLAB. In that, when it is an GUI, when you are preparing, that is graphical user interface, it is some blocks are there, right? But inside that, you are writing lot of things. But whenever, as a person, when I'm seeing that GUI, so it gives everything information about that what is needed. But I don't want to go to the detailing of that. So it is like Simulink, you just take a block, right? Exactly. What is there inside that we don't know now. But when you connect this, it becomes a system. And that is the way of abstraction. And the other way is like whatever you write an abstract for your thesis. Yeah. So that gives you the detailing. That is what the view through this abstract only you will get to know that what is there in that particular thesis. Yeah. So when you talk about an abstract of a document or an abstract of a tome, like a thesis, then you're bringing out the essentials and you're not going into the details. That is true. Correct. Yeah, very nice. Thank you, Professor Somani. Anybody else? We'll take one more. That's all. All right. Now, if we, I'm very happy. I spent a little time. So, as I said, I'm not going to rush through. You know, if necessary, we'll, carry this discussion to the next session also. But, let us now go on to the second presentation. And there I have group 2 making the presentation. So I have, now group 2, I would like one of you to come forward, introduce yourself and your group, and then proceed with the presentation.
Good morning, sir. Good morning,
very good morning
to all the faculty members. Sir, I'm Dr. Smita Elsa Peter. Sir, good my group. Yeah, I will just share my slides, sir. Now.
Yes.
Sir, the members in my group are
very good, very good. Yes.
Myself, Dr. V. Prema ma'am, Dr. Meenakshi Atre ma'am, and Professor Manisha.
Yes.
Sir, is my screen visible, sir?
Yes, it is. It is. Yes.
Yeah. So we have been allotted some definitions part of the lecture, sir, the second lecture.
Madam, just before you go ahead, isn't Professor Manisha Dwivedi also a member of your group?
Yes.
No. Yeah. You mentioned. No,
yes. 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 Sir, actually, we have Professor Meghna also allotted in our group.
Yes.
But she has not joined. So she has not joined, sir.
Okay,
I was also checking. Yeah, we were checking that up, and she has not joined. So it seems she has not continued in the group. I think so. She has not joined
the. Not as a participant because we received her nomination. That's okay.
Yeah. Yes, sir. Yes, sir. Yeah. So we are just now 4 members, sir.
Yes. Please.
Yeah. Okay. So I shall present my slide. Yeah. So the agenda is. We go about it like this, sir. some definitions deals with signals, systems, system description, and additivity. Signals will be presented by myself. Systems will be presented by Dr. Prema ma'am. System description by Dr. Meenakshi, and additivity by Professor Manisha. Right, sir. So I go on to the signals part of it, which will be presented by myself. Sir, with regards to signals, on a more generalized method of defining signal, signal is a time-varying voltage or any other quantity that generally carries some information. But when we mathematically try to talk about signal, the definition for a signal is a function of one or more variables that conveys information about some physical phenomenon. For example, if you take a function f in the expression f of t1, t2, etc. up to tn, each of the variable tk is called an independent variable, while the function value itself is referred to as a dependent variable. Some examples of signals may include a voltage or current in an electronic circuit, the position, velocity, or acceleration of an object, a force or torque in a mechanical system, a flow rate of a liquid or a gas in a chemical process, a digital image, digital video, or a digital audio. So, in brief, a signal is a function of one or more variables that conveys information about some phenomenon. Signals may be classified as continuous time signals or discrete time signals. Now, for further presentation will be carried by Dr. Prema ma'am.
Good morning, one and all. So my part is describing a system. By basic definition, a system can be considered as a mapping from set of signals to another set of signals. That means any system can take an input signal and process it and give another signal as an output. So this is basically the definition of a system. Now going to the examples of a system. First example, this is the first example I take in all my first class in my signals and system, a human body. So if you take a human body, you have several systems inside a human body. For example, if you take your auditory system, the sounds, suppose if somebody is telling you to take a pen from the desk. So the input to the system is the sound signal to take the pen. And this input signal is converted into electrical signal and it goes to the brain, and the brain processes the signal, and the brain sends the signal to our hand, basically through the nerves, to take that pen. So automatically our hand lifts and take the pen. So this is one example of a system. So system is your auditory system in your brain. Similarly, you have digestive system where your input is the food intake and the food is getting processed inside, and then your excretion is the output. Like that, if you take any system in our body, you can take one as an independent system. So your human body consists of several systems. So this is one example generally where I take in my class. Similarly, you have a microphone. This is another example. So where some acoustic signals are the input, and basically these acoustic signals are mapped to a set of electrical signals which are coming out. So basically, signal is a mapping. System is a mapping of signals, various signals, maybe the input signal and the output signal. And how you map the signal will be the property of the system. Similarly, there are many other examples in real-time world. Can you just go to the examples part again? Yes, an electrical circuit where you have any electrical component like R, C, or L in the circuit, and voltage signal is the input, and current through the load or current through the resistor or RC network will be the output of the signal. Similarly, you have a camera where the light from different positions will be the input to the camera processes it, and the output will be the photograph what you obtain from the camera. Similarly, you have an automobile. So can anyone say what can be the, if I take automobile as an input, what can be the, as a system, what can be the input to the automobile and what is the output? Can anyone say?
You can ask them to put it in the chat.
Yeah, you can put it in the chat. So by automobile, you can take any vehicle, say two-wheeler or four-wheeler or anything. speed is the output. Yes. What could be the input? Pressure, or you can say that the pressure you apply to the accelerator can be the input. Fuel, you need fuel also to accelerate it, but basically the input here we can consider as the pressure applied to the accelerator, and then the speed of the automobile or movement of the automobile can be taken as the output in a simpler way. Similarly, an aircraft landing system also is a real-time example of a system. So with this, I am handing the presentation over to the next person who is going to give the system, the definition of a system or system
description. Okay, thank you, ma'am. This is Meenakshi Atre. So this presentation is about the description of a system. So the picture itself is self-descriptory, self-explanatory, we can say. So here there is a transmission and there is a reception. So we consider the example of communication system. So this system consists of the transmitting device and the receiving device. And apart from that, the tower that we are seeing. So the input would be a signal, which is typically a speech signal. So that will be transferred. So how we can say that output will be produced? So output will be a function of the input. So inside the function, we can say it's nothing but the modulation technique, right? So we have the modulation as the processing element of this communication system. So when we talk about the system description, there are few keywords like mapping of a signal to signal, as sir mentioned. We can also call that output is a function of the input. We can also say that it's the transfer of the input signal to the output. So best is nothing but the transformation of the given set of input signals into the output. So these are the keywords like mapping, it's like function, it's like transfer, and we can say juggle between these words like mapping function or transfer function, like say h of s or h of z, like that. So it's all about how do we describe a system, and this description always need some function. So it may be h of z or it may be h of s. Okay. So talking about the system description, I would like to give the example of the workshop, that is pedagogical workshop. Right now we all are in. So imagine we all are nothing but the elements or the inputs for this workshop. And we are like students for this workshop, and we will be converted as the teachers with the pedagogy or more aspects of or elements of the pedagogical aspects after this workshop. So it's like the function of the pedagogy that we are into. So we will be transformed into better teachers with the function of the pedagogical aspects that will be given through the workshop, or that will be given through Dr. Gadre sir. So you can see this picture has a different orientation of the faces. So after this workshop, we all will be aligned, we all will be polarized, and that's nothing but that's nothing but the output of this workshop. So that's about the system description. Now I request the Manisha ma'am to explain further. Thank you, sir.
Thank you, Meenakshi ma'am. I'm over here to explain additivity. Now, we have a system over here wherein we are performing an experiment. This experiment is having an input as x1 of t, which results in a particular output y1 of t. Then there is a second experiment which is being performed, that is x2 of t, wherein it results in an output y2 of t. And the third case is where we are adding the two inputs. That means we are clubbing the two experiments together, and we are now giving the input as x1 of t plus x2 of t, which results in the combination of the outputs that we have achieved in the first two experiments. So if this case is satisfied, we say that it is an example of additivity. Now, to explain this concept in a more clear way, we have taken two examples over here. We go to the example. In this case, you can see this is true for all the inputs and all t. So here we have taken an example where we have y of t is equal to 2x of t. It means that when I am performing the first experiment with an input x1 of t, it results in an output 2x1 of t. So the outcome of the experiment is y1 of t, which is 2x1 of t. Then we perform a second experiment with an input x2 of t. wherein the outcome of this experiment is y2 of t, which is equal to twice x2 of t. And then we combine both the inputs. As we combine both the inputs, you can see that my output will be twice into bracket x1 of t plus x2 of t, since I'm taking the combination of the two inputs of two different experiments. So this results in 2x1 of t plus 2x2 of t. And 2x1 of t is nothing but output 1, 2x2 of t is nothing but output 2. So when this condition gets satisfied, that when we combine the inputs, the output is also the combined output, we say that this is an example of additivity. Now we move on to the next example. In this example, we have taken the outcome of an experiment as x square of t, that is square of the input. So first we perform the experiment with a particular input x1 of t. There, the outcome of it, we get it as x1 square of t. Then we perform a second experiment with input x2 of t, where we get the outcome as x2 square of t. Now we are combining the input x1 of t plus x2 of t. So in this case, you see that we are getting the new output as x1 of t plus x2 of t bracket square. So this clearly shows you that this is not equal to the individual outputs, that is x1 square of t plus x2 square of t. So this gives you a clear indication that this is not an example of additivity. So it is non-additive example. Now, relating it to the real-time example, we can compare this to an orchestra where the different instruments, the frequencies or the music coming out of an instrument is getting added to the singer's voice. So this could be related as a real-time example with additivity property. So that's all for now. Thank you so much.
Thank you very much, Group 2. I was delighted to hear your presentation. So maybe you can now stop sharing so we can now discuss your presentation. So let us congratulate Group 2 for a very nice presentation indeed. Let me now point out some very good features of this presentation. Point number 1. You see, this presentation was done by the group and the whole group participated. This is something which we should appreciate for all of them. They made such a beautiful presentation by sharing the presentation so effectively. It was seamless. The sharing was seamless. So they really made an effective plan for the presentation, and all this was done, I'm sure, in a very short time, perhaps in a day's time. And
we had floated a Google slide, and this Google slide was shared with all of us, and we were parallelly editing the presentation.
Oh, very good. Yes. So, now they also made use of online editing tools. That's something that we should all appreciate. And in fact, these are the things that we probably in this online teaching and learning situation, these are some of the things that we must appreciate, about this presentation. Moreover, you can see that they were very, very concise and very, very clear in what they wanted to bring out in the presentation. You can see that they more or less stuck to the time that they were assigned, and they never was there a dull moment in the presentation. There never was there a dull moment in the presentation. We were all the time all ears and eyes to listen to the details of what was being presented. Thirdly, if you look at it, as far as additivity goes, they gave both an example and a counter example. It's always good to, whenever you're trying to explain an abstract idea like additivity, both an example and a counter example help. And they did that, an example and a counter example. Fourthly, I like the idea of the orchestra. I also like the idea that pedagogy was a system. The pedagogical workshop is like a system which takes all of you as inputs. Of course, there I wouldn't call it, but you can call them discrete. You can call them discrete inputs located at different points in space, and each of them is then transformed to the same people in the same region of space. But of course, after this pedagogy workshop, that was a very interesting example of a system, a discrete system, of course. And the final example of bringing additivity to illustrate the orchestra, where you have the musical instruments and the person's voice, the voices of the chorus, that the human chorus and the musical instruments which come together, Of course, people can have different views. It could be additive or non-additive depending on how finely you're looking at the way these two sounds combine. But broadly, the idea is important. You could be listening just to the musical instruments, or you could be listening just to the chorus, human chorus. And when you come together, you're really adding the two effects depending on the level at which, the sound levels and so on. So that's a very interesting example. So very good, a very nice presentation. Now I will invite a couple of critical reviews of this presentation from the other participants. Yes. So anybody who would like to make a critical comment on this presentation? When we say critical comment, it doesn't have to be negative criticism. It can be constructive criticism, constructive praise, and so on. Yes. So any volunteer to make a critical comment? Yes.
I'm Lekha Das. The examples were real-time examples, so it was easy to understand the situations.
Very nice. Very good. That was a good thing that they did.